Yes.
3.2 minus 2.9.
Who will be?
So I'm glad you asked that. Here we're looking at making a one-to-one correspondence between the natural numbers and the set that's 6 times the natural numbers, so the multiples of 6 in this case. You probably have a different one. You maybe have multiples of 4 or multiples of 3. So we made a one-to-one correspondence in class by letting the 6 go with the 1, the 12 go with the 2, the 18 go with the 3, the 24 would go with the 4. So it turned out each natural number went with a number that was a multiple of it. To type that in here, you use the star button that's on the 8th key, okay? And that's what that's trying to get at. So there's not a good way to draw the double arrows on this to show your one-to-one correspondence, so we instead show it using the algebra here. Any other questions? Okay. I did want to look a little bit at the textbook. This is George Cantor, who brings us set theory. He was alive in the late 1800s. His proof that there were infinities larger than other sizes of infinity really was counterintuitive, and the mathematicians of the time gave him a very difficult time. Let's see what your textbook writes. When Cantor conceived his idea near to the end of the 19th century, many mathematicians resisted it strongly and attacked Cantor in a personal, abusive manner. These attacks, combined with other psychological issues, contributed to a bleak existence for Cantor, who spent much of the last part of his life in an insane asylum. So the ideas that we're looking at, that some infinities are bigger than other infinities, is a difficult concept, and even the mathematicians didn't accept it all readily and run to Cantor and say, oh yes, what a marvelous discovery you've made. Now 100 years later, more than 100 years later, the mathematicians all look at his ideas and say, well, of course, they make perfect sense. But at the time, it was a new idea. So in 3.3, we finally look to find the set that is larger than the natural numbers. When we do that, considering larger sizes of infinity like that, we're considering the counterintuitive. So that's a life lesson, and that's what Cantor did. He considered the counterintuitive and not just considered it, proved it possible. So we looked at lots of possibilities for for infinite sets that were bigger than the natural numbers. Excuse me. We looked at the integers, z. We looked at the rational numbers, q. But these sets all turned out to have the same cardinality. They were the same size as n. So remember how we did that. We always go back to our definition. We look for a one-to-one correspondence. Okay, I'll put my fingers together here. A one-to-one correspondence between elements in one set with another to show they're the same size sets. And that's what we were able to find. showing a set is larger than the natural numbers. Showing a set is larger than the natural numbers means that we will not be able to list it, that it is impossible to list that set. So we're going to look at that later on today. In order to do well at that, we actually have to go back to the game we did the first day of class, dodgeball. Remember, player one wants a match. Player two wins if there's no match. And by a match, I mean a roll that matches player two's roll. So player one wants their row to match player two's row. So I'm going to be player one, and you can tell me if you remember what player two should do here. So what should player two do here?
Avoid any of the possibilities of the
Yes, and how would they avoid that for row one? What should they put in column one?
Oh.
Yes, oh, good. So player one wants a match. What should player two do in this case?
Oh.
Oh, good. Okay. There. That's enough O's. What should player two do in this case?
X.
X. Okay. And how about in row four?
Oh.
Oh, well, I can see you're remembering very well. Now what?
Yeah, X.
Yep, good. And now what?
No.
Oh, that's me, isn't it? Okay. All
Oh,
right.
and X, yeah.
X. Okay, good. Okay, so I can see you were remembering. You were focusing on the first column for player two's first position, always being different than the first column in the first row. And then in the second row, you made sure you were different from the second column. In the third row, you made sure you were different from the third column. In the fourth row, you made sure you were different from the fourth column. In the fifth row, you made sure you were different from the fifth column. And in the sixth row, you made sure you were different in the sixth column. So that's actually the basis of Cantor's diagonalization proof, because if you're different in just one position, you'll be different from the whole row. So his focus was on being different in the first column in the first row, second column in the second row, and so on. Now, to make sure you know how to do this, I'd like you each to play as player two again in dodgeball. So I'll hand out some dodgeball playing boards. Online students, you can go ahead and print this out and make sure you can win as player two so that you're able to do this well. So this is on the Canvas homepage if you have to print it out. And Nicholas, you'll get to play if nobody has a partner. So let's see if I can pair people up. Yeah, actually, let's see. Actually, if you mind going over here, can you please put your name tags out again here today? If you don't have a name tag, I'll just do mine. Okay. So Max, if you wouldn't mind going and playing with JC, that'd be great. And you can, Nicholas, you can walk around and help people if they're stuck. So raise your hand if you're stuck. And everybody should get an opportunity to play as player two and win. So make sure you play twice at least.
So I need to create something then?
You're trying to do the same thing that I'm trying to match to when you want to make it match to me.
I was.
So, you maybe didn't lose the strategy. Always do the opposite. Yeah, always do the opposite. Because that way, you won't match this row to that one. You won't match this row, this one. You won't match this row, this one. So you might have other cards matching, but those that Did player 2 win both times? Yep. And you didn't win the characters left with player 2? Did player 2 win? Were you using the guys?
How would you boss it?
Yeah?
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 Yeah? Yeah.
Did player 2 win both times?
That's impossible. Unless somebody do like some kind of trick in the beginning play again.
You can go back to your seat. A
A
class nap. I used to have a student that would nap during class regularly. I'd just be looking at him, he'd be snoozing away. And then I didn't really worry about it. I mean, he's paying for the class if he wants to use it to nap. Then during the final exam, he napped off. He was sitting there taking the final, and he's sitting there sleeping. Well, maybe I should wake him up now. That was something.
Did he pass?
Yeah, I know. He must have just known the material. Okay, so we're looking to be different from the first row by being different in the first column, different from the second row by being different in the second column, different from the third row by being different in the third column, different from the fourth row by being different from the fourth column, and so on like that. And so that way player 2 can always match. And I saw you were getting the hang of that, so now I'm going to make it harder. Okay, what if can player 1 win if player 1 gets to list as many rows as they want? Before player 2 lists anything. So player 1 can list whatever they want before player 2 lists anything at all, and then player 2 makes their roll. So player 1 lists rows and rows and rows, as many as they feel like. And then player 2 gets to try and make one that doesn't match. How's that going to work?
Player one's gonna win.
Yeah, player 1's going to win. Why would player 1 win?
Because they can list like every possible row.
Go ahead. There's only 64 possible rows. So if you listed all the different X and O combinations, there's only 64 of those. Because there's 2 different things, you know, you can put an X or an O in each box, and there's 6 boxes. So that comes out to 64 possibilities. So if player 1 carefully lists all those possible rows, then when player 2 comes along, there's nothing they can do. They're going to match. Okay, well, let's make it harder then. So that was too easy. Okay. So we found a way player 2 can always win. And now, if we modify the game, player 1 can always win. But what if we modify the game in a different way? So we're still going to go back and forth taking turns. But now, could player 1 win if there were infinite rows and columns? So infinite rows and columns. So let's see, the little board would look like, just keep going like this, dot, dot, dot. Each row, dot, dot, dot. Well, player 2's row would have to be infinite too then. So can player 2 still use the same strategy and be different? Maybe, since you just think, well, taking one row is going to take forever. So how would player 2 even get a chance to play? Let's think of it this way. Suppose player 1 lists those infinite rows and columns right off the bat. So player 1 lists them all. So player 1 makes the list. That finishes player 1's turn. So player 1's sitting there with the infinite long rows and infinite columns. Well, I guess that makes sense. Infinitely long rows will get infinitely long columns and an infinitely long list. So row upon row upon row, infinite rows. And then player 2 takes their turn. Will player 2's strategy still let them win? Well, let's think about it. If player 2 takes the same strategy and looks at this list of X's and O's, these are all listed out, 1, 2, 3, 4, 5, 6, and so on, so they can still focus, player 2 can still focus on the first row by being different in the first column, right? So can player 1 be, I misspoke. Can player 2 be different from the first row? Even if it's infinitely long row? Yeah. Okay. Can player 2 be different from the second row, even if it's an infinitely long row? Okay. So can player 2 be different on the 10th row? In the 10th column? Yeah. So player 2 can just keep up this strategy and always be different from any particular row by looking at that diagonal column there. So on the 100th column, if player 1's 100th row has X in the 100th column, player 2 will have an O there. On the 500th row, when player 2 goes to put their 500th column down, they'll look at the 500th row and be different from that 500th column. So they're just focusing on the diagonal all the time so player 2 can still win. So that's kind of interesting. We have player 1 making an infinite long rows, infinite columns, finishing up. Player 2 takes their turn, and player 2 still wins by following the same strategy. What that means is that player 2 found a row not on the list. Even though player 1 listed an infinite number of X's and O's, player 2 found a row not on the list. That means that the list of possible X's and O's, if you make it infinitely long like this is a set that's bigger than the natural numbers because it cannot be listed. We found one that's not on the list. It's impossible to list all of these possible combinations of X's and O's, because if you say, okay, I'm done, I've listed it, player 2 can find one not on the list. So there's our first set that's larger than the natural numbers. Let's think about this further in terms of the real numbers. So, looking at real numbers. Guess I can make it large again. Consider the real numbers. Those can be abbreviated with a capital R with a double bar. Remember, those are all the numbers on the number line. Those are all the numbers on the number line. So we have numbers like pi, put dot, 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 because that's all the digits my calculator is showing. We have numbers like 2/3, we have numbers like 5 or 0.25. Every real number can be written with infinite decimals. Okay, so every real number can be written with infinite decimals. So this number 5, for example, you would write 5.00000000. Or 0.25, you'd write 0.25000000. So real numbers, each real number can be written with infinite decimals. These real numbers are going to be our candidates for being a set larger than the natural numbers. When we list them with our infinite decimal expansion, they're going to be like listing our rows that go on forever and ever. Now, let's see how we can find numbers that are different from one another among the real numbers. So on this number A, I'll call it A, it's 0 point, and then I blocked out with X's most of the digits. So 3 digits are blocked out in the decimal expansion, then there's an X, and then there's more digits blocked out. Find a number between 0 and 1 that you are positive is not the number A. So you only know one digit in A's decimal expansion, but I'd like you to find a number between 0 and 1 that you're positive is not the number A. Mm-hmm. 0.5. Okay, so 0.5. And how do you know it's not the number A?
Because after that, it's just a bunch of zeros.
Good, because after that it's just a bunch of zeros. So it does not have a 7 in the fourth decimal place. Good, so if you wrote down a number and you made sure there was not a 0 in the fourth decimal place, then you did it. You wrote down a number that you were positive is not 8. Let's try another one.
Can you bring it up, please?
Thank you. So we're going to look at B. Find a number between 0 and 1 that you are positive is not B. Find a number between 0 and 1 that you are positive is not B. Point 25. 0.25. Okay, so you're saying that ends in zeros as well? Okay, good. Yeah. So that's one way to do it. So whatever number you wrote, as long as in the third decimal place there is not a 2, then you know your number is not the number B. So we're looking at sets that are larger than the natural numbers, an infinity larger than the natural numbers. That's what we're looking for. Now remember, if a set is the same size, if a set is the same size as the natural numbers, then its elements can be listed. If a set is the same size as the natural numbers, then its elements can be listed. Remember, we saw that with the set of integers. We had to come up with a way to list the set of integers. Does anybody remember how we were able to list the integers without missing any or using any twice? So we did the set of natural numbers, and we said that Z, the set of integers, could be put into a one-to-one correspondence. Does anyone remember how we arranged these so we didn't miss any or use any twice? Yeah.
Do you know like alternate?
Mm-hmm. Good. Yep, we did. We started out with 0, and then we alternated like that. So the integers were in a one-to-one correspondence with the natural numbers, and we could show that by just finding a way to list the integers without missing any, without using any twice. And we did a similar thing with the rational numbers. We found a way to list the rational numbers without missing any, without using any twice. That was more complicated though, right? Remember we had to do this whole spiral thing and make all these columns of all the fractions. So that was a little more work. So if we find a set that it's impossible to list, well then it's not going to be the same size as n. So the natural numbers are the set that we're headed towards showing that it's impossible to list. So to show that it's impossible to list them, we will say, well, what would such a set look like? So your book has one listing. So if it were possible to list the set of real numbers, it'd look something like this. If you could do this. Okay. So you have some negative numbers, you have some positive numbers, you have some numbers that are smaller than 1 and greater than 0. But each one is listed with an infinite decimal expansion because every real number can be listed with an infinite decimal expansion. Well, we're going to use our list that I made to do Cantor's diagonalization proof. We're going to take this list and say, well, suppose this is all the real numbers listed. It's infinitely long, so I can't show that. That'd be too crowded. What would a missing number look like if it wasn't on that list? So this would be a likely quiz question, and we would say, use Cantor's diagonalization method to find a number we are positive is not on this list. Use Cantor's diagonalization method to find a number we are positive is not on this list. And I might put the word dodgeball in parentheses there to remind you of how we're doing this, okay? Use 4, if not 4, else use 2. So that's what Cantor's genius was. He just is going to come up with a missing number, and we're going to follow his idea here. Come up with a missing number from this list. So start the number off with 0, and we'll just be focusing on the decimal expansion, and that's why we start with 0. We don't want to start without the 0 decimal point, because otherwise we'll just get a very large number, not a number between 0 and 1, and the diagonalization proof is going to focus on the decimals, so we need a number between 0 and 1. So what Cantor did, he's just brilliant. He said, okay, we're going to look at the first decimal place and be sure we're different from the first number, because if the first decimal place is a 4, then I'll put a 2. If it's not a 4, I'll put a 4. So in this example, the first decimal place is a 2, so we put a 4. So we know now we don't match the first row. Now in the second row, we look at the second decimal place, and it is a 4. So because it's a 4 and we want to be different than the second row, in the second decimal place, we pick a 2. Now we're being very careful, right? You could have just said, well, I just I know I'm smaller than negative, I know I'm not going to match this because I start with a 0 and this is a negative 24. But remember, we're coming up with a pattern that's going to work where the dot, dot, dots are, where we can be sure that we're not matching even though we can't see the numbers. Okay, so in the third row, we look at the third decimal place. Third decimal place is 8, so I go back to the 4. So we're always using 4 unless that decimal place is a 4. Then we switch to a 2. Now I'm on the fourth decimal place. 1, 2, 3, 4. That's a 3 in the fourth row. So to be different from the fourth row, I'll stick with my 4 in the fourth decimal place. In the fifth decimal place, I look at the fifth row. 1, 2, 3, 4, 5, and there's a 4 there. So I don't want to be like row 5. So in the fifth decimal place, I'll put a 2 because there was a 4 there. Now in the sixth row, I look at the sixth decimal place. 1, 2, 3, 4, 5, 6, and there's a 2 there. So I can use my 4, my fallback number. So I'm always using 4 unless that decimal place is a 4. Then I switch to a 2. And in that way, I'll always be making a number that's different from that row. Did I do 7 yet? No. Let's do 7. 1, 2, 3, 4, 5, 6, 7. So there's an 8 in the 7th decimal place. So I'm going to go back to my 4. And then I don't know what's going on in the 8th, 9th, and 10th rows, but I know I'm not going to match the 8th, 9th, and 10th rows even though they don't show because I have this pattern going. I'm going to not match the 8th row because in the 8th decimal place, I'm not going to match the 8th decimal place in the 8th row. In the 9th row, I won't match the 9th decimal place, and so on. So now we're on row 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. In the 11th decimal place, there's a 3. So I go and put my fallback number 4. If this had been a 4 instead of a 3, I would have picked 2. Okay, so I'm always picking 4 unless that decimal place is a 4. Then I pick 2. So I put dot, dot, dot to mean that I'm continuing this pattern, so I'm not going to look like row 12 or 13 or 14 because I'm going to differ by 1 decimal place in each of those for sure. I might differ by more, but for sure I'll differ by 1 decimal place. So this is a number that's missing in the list. So if there was a way to list all of the real numbers, we found that there isn't. Because if there is a list, then it's fixed and it's done. Then we can say, but wait, you missed this number. This number is not on that list. I'll give you another chance to try this, because like I said, this would be a good quiz question. So I'm going to have you do the same thing with this other set. Take another piece of paper here. Okay. So use Cantor's diagonalization. To create a number between 0 and 1 that we are positive is not in this list. Use 4 if not 4. Else use 2. Okay, so go ahead and create that, and I'll create it too, and Nicholas will create it, and then we'll walk around and see how you're doing and make sure you're getting the hang of this. Don't forget to start with 0 point something. If you're stuck, raise your hand, okay? Or if you think you have it, raise your hand. Yeah, that's what I have to talk about.
Is it the same one that we just had?
If it is, it's on accident, but it might be.
I think so.
It might be. I don't know. If it is, it's on accident. Yeah, is it the same? And did you do the 11th one? You got the 11th one, okay. So here on the fourth row. So what digit is in the fourth decimal place on the fourth row? Oh, is it too tiny to read? Okay. Okay. So it's a 0. Okay, so if it's a 0, then what would you put that? Okay, so yours you just put C.
High school.
So you want to do that. Yeah. Okay, good. Now you're on the third one. So what do you think on the third one? There. So hopefully you remembered the 0 points. If you don't remember that, then you're not going to be between 0 and 1. And also we need that 0 point to be able to focus on the decimal place we're on. So to be different than the first decimal place in the first row, we're going to use our fallback number 4 since there's a 3 there. Second decimal place in the second row is a 4, so we go to using a 2. So we're going to be different from the second row now in the second decimal place. In the third row, in the third decimal place, there's an 8. So to be different from the third row, we put a 4. In the fourth row, in the fourth decimal place, there's a 0, so our fallback 4 again. Fifth row, fifth decimal place is a 4, so we use a 2. So we're going to be different from the fifth row. 1, 2, 3, 4, 5, 6. In the sixth row, in the sixth decimal place, there's an 8, so we're using our fallback number 4. So we keep going like this, and we continue so that we are always different in the nth decimal place in the nth row. Now, you might see this as kind of like simplistic because you can see those numbers and you can just pick a number that's different. You could just pick the number 5, and 5 is different than all 11 numbers. But the point is that we have numbers that are not here because this is an infinite list. So we need a pattern to continue. We need a pattern to continue that assures us that we are finding a number that is missing from the list. And this is Cantor's diagonalization proof. He came up with this idea, and it does in fact find a number that's not on the list. So the real numbers cannot be listed, and the set of real numbers has a larger cardinality than the set of the natural numbers. Well, this is as far as I got with the first class, and so here's where we'll leave off as well. If you have time to practice this, this would be the type of problem to practice for the quiz. It's not on your Mindscapes on the homework very well, but it is in the textbook Mindscapes. I'll see you on Monday. Have a good weekend. Oh wait, this is what you need to take a picture of for your class activity too. Yeah, so this number that you just made, that's your class activity for section 3.3.